Swayam Prabha. Digital India. Educated India.
Welcome back. We are going to do a new molecule in this wheel. We're changing the hub here. We're changing the center of the axle here. And what are we changing it to? We're changing it to this downward dog here. You know, if you're doing yoga, this kind of looks like a downward dog. But this is a molecule where you have a double bond that's tri-substituted. Let's look at the name here for a second. You can number it this way or this way, but since you have a substituent here, we should go this way. 1, 2, 3, giving the lowest possible number to that alkene. 4, 5, 6, so it's a 3-hexene. So it's going to be 2,3-dimethyl hex-3-ene, but we got to say what it is. Is it an E or a Z? Well, this is the higher priority and this is the higher priority. So they are on opposite sides. So that's trans and E. So that's going to be 3E, 2,3-dimethyl hex-3-ene. All right. So I don't have space to write that down. I hope you got all of that. All right. Let's look at it and see what reactions are going to happen on this and how. We have osmium tetroxide and KMNO4 cold. They both do pretty much the same thing. So I'm going to write, the products here. And this time, let's try to draw minor products if there are, and if we have space. All right. Let's look at this one. So here you have a pi bond. Pi bond's got two faces, above and below. So osmium tetroxide can go above or below. And then when you hydrolyze it, you can get diol above or below. Throughout it all, we're not rotating the pi bond. So the configuration stays. So in all of the products, this isopropyl group will be on the opposite side of this ethyl. That's really key if the reaction is stereospecific. All right, so if it's in an anti, that's going to really affect that. So make sure that these groups that are on opposite sides stay on opposite sides. If it is a trans, if it's a cis, then you put them on the same side. Let's do a trans here. So one of the ways to draw that is to make sure that the ones that are on the same side are coming out as wedges, and ones that are on the opposite side are going in as dashes. That's one way to draw it. Now, the hydroxyls are going to go both on the same side. They can both go above or they can both go below. And even when you're drawing the other one, make sure you keep the same configuration. We can tilt these up a bit if you'd like, because you're going to put the hydroxyls down. And in no time during the transition state or intermediate are we rotating that pi bond. So the absolute configuration is maintained. Now, is there any other way to draw it? If I put the groups that are going back in front, and here's a hydrogen which I haven't drawn there, and the groups that are going in front at the back, like this, the ethyl group at the back, and then I can put the hydroxyl up. Why don't I do that? Is it the same thing? Well, if you look at that, you can take that and flip it over, and that's exactly the same thing as this. So if I do a 180-degree rotation or flip, this is going to be the same thing as this. So there are two ways in which you can draw this. You can keep this absolute configuration the same, put your hydroxyls up or down. Or you could keep the hydroxyls on the same side and flip these groups. The ones in front can go to the back and the ones in the back can go to the front. They're going to be exactly the same thing. All right. So I'm just showing you what are the two ways in which you can draw it. And I'm just going to put the hydrogen here just for good measure here. So here's your hydrogen and here's your hydrogen. Hydrogen is in the same side as the isopropyl group. So just bear that in mind. So there you go. So there are two ways to draw it. Let's look at the BH3 here. So the BH, again, we know it's governed by sterics. This big bulky boron, BBB, is going to sit on the tail end because there's no steric there. This guy doesn't have a tail. and the hydrogen is going to go wham, bam, hit that neck over here. Okay, there's more steric here. That is going to then pull the hydrogen down, and then the pi bond is going to be pulled by the boron here. And they're going to go on the same side because it's coming together on the same side. So there's your next syn. All right, so then we are going to draw your product. Your boron is going to go up, and then it's going to get oxidized to the alcohol. And if you haven't seen the previous one with the 5-membered ring, just please watch that because I drew all of the intermediates on that. And here I'm just going to go to the product right away. And because I got to also draw the minor, I really don't have space to do all of it. So here is your hydrogen going on this carbon, and going to go up. And your hydroxyl is also going to go up. There's a hydrogen going inside here. Or you can have them both go down. So here are your groups, and we're not changing them. Hydrogen is going to go to the most sterically hindered, most substituted carbon, exact opposite of Markovnikov. So this is an anti-Markovnikov. Boron goes to the less substituted, and then it gets oxidized by the peroxide over here. So what are these two? Well, looking at it, it's pretty obvious. You can take a mirror, put it over here, and you're going to see exact same thing here. So these are enantiomers 1-to-1. Well, what about the minor? Would there be a minor? Well, there could be a minor where your hydroxyl goes on the other side, but most of the time it's going to be a syn addition. You won't see anti-addition. So your minor would be where you're going to have hydroxyl go over here and hydrogen go over here. So that will become achiral, and this would be your chiral. So you would have OH down and OH up. So that is going to be 1. And your other one is going to be this coming out and your methyl going in. And this is anyway going to become an achiral just because you've got 2 hydrogens now. As you can see, it's pretty obvious. One is R and one is S. And so that's going to be an enantiomeric mixture as well, a 1-to-1. You can get the other regioisomer as your minor product. But for the most part, your stereospecificity would remain because of the way the reagent is built. All right, let's look at Cl2 in aprotic, and in this case, nonpolar, and Cl2 in protic. What are the differences? The differences could be a lot to do in the minor product, but the major product would be very similar to what you had before in terms of stereochemistry. Again, just draw it just the way it is. So these are going to be your groups coming towards you, and this is your group going away from you. And draw the other one also. So you can have this going back. You're going to have that. And your chlorine will go on opposite sides. So if it is going up here, it'll go down here. And if it's going down here, it'll go up here. All right, what's the relationship? Same question every single time. So, and what's the relationship? Well, you can see it's going to be anti-addition. And you put a mirror right here, it's going to exactly reflect this. So these are enantiomers 1-to-1. Now, what's the minor product for this? Rarely do they see syn addition, and rarely do they see carbocation rearrangements. So really, you may have a low yield, but the distribution of this will be pretty much your major product. Let's look at this. Most of the time, when you have Markovnikov, anti-Markovnikov, it's easier to predict minor product. But when you have very stereospecific reactions like this, there is no way chlorine can actually go on the same side, syn. Now, if you had a triple bond, chlorine can some of the time go syn, and we really don't understand that mechanism. But on double bonds, they go anti. let's look at this. So here again, we do the same thing. What's on the same side, draw it on the same side. And what's on the opposite side, let's draw it out like this. And chlorine is going to go and make a triangle here, chloronium, and your water is going to do a Markovnikov. It's going to attack right here, more substituted. It's not really going to prefer to attack here because this tertiary center can bear that positive charge a lot better than the secondary center, and we talked about it. So over here, you're going to get attack of alcohol or water here and here, not here. That's Markovnikov. So the chlorine's always going to roll over here. So your alcohol, and let's make up an alcohol here, isopropanol, it's going to come over here and attack here. So that is going to be attacking that and roll over chlorine. Chlorine's below, it attacks from above, and there you go. So that'll be your major product. What's the relationship? I'm sure you got tired of me asking these, but we just have to always compare your products. If you put a mirror here, this is going to get reflected exactly like this. What's on top will be at the bottom. What's on the bottom will be on the top in the mirror. In this case, you know, these are just going to reflect above, will be below, and below will be above. So these are enantiomers 1-to-1. Raceme, it is regiospecific. So the minor product here can be where your chlorine is going to be on this side and your alcohol is going to be on this side. So same thing as before. So in both cases, the chlorine can be in the most substituted position like this, and your ether bond can be on the opposite side. You do see a little bit of the minor product having the opposite regiochemistry. So this is, again, as we mentioned, minor products. These are your major products. MCPBA, well, MCPBA is always going to form on the same side. So your oxygen can be on up or down. And, well, are they the same molecule? If I take this and rotate it, will it be the same? Or can I somehow turn it around and superimpose it? Not really. If you flip it 180, these are going to go in. And we don't see that here. They're still out. If you put a mirror right here at the bottom like this, you're going to see this molecule right here. So these are both enantiomers. And what's usually the minor product here? Minor product is typically when you don't distill your dichloromethane or you have atmospheric moisture. You also have to cool this reaction, so you may have condensation. And your minor product is usually in these reactions the diol, the antidiol, from water getting into the system. And it's going to be OH and OH plus the mirror image plus enantiomer. That's going to be a minor product usually. What would happen if you made the epoxide and then hit it with some protic solvent? I mean, it could be this. You could also have other things, or you could say amines. Let's do an amine since we've already done an alcohol and water. We could do other nucleophiles. Let's do an amine. So you're going to get one of these, and since this is in a protic solvent, you're going to get protonation of these two, which makes them electrophilic, and so they're going to be tugging at those electrons. And when you tug at those electrons and you have a tertiary center, that's a lot more stable than a secondary center, a lot more stable. So you are going to get attack of the amine here rather than here. So it's very regioselective in that sense. So here we're going to get the same thing initially, which is the epoxide. And now you're going to get the epoxide being hammered by the amine and roll over epoxide to make way for the amine. So in both cases, you're going to have the amine attack at the most substituted carbon, and then it gets deprotonated. And let's say the amine comes with some R group, and the R group is like an ethyl or some other group, and you're going to get that. And your oxygen is going to go down and get protonated by the acid. And you would also get attack from above, as in shown here, or attack from below. And so you're going to get your nitrogen here. If it attacks the most substituted carbon, your oxygen is going to roll over and get protonated here. So these are the two things that you would see for major products. And what's the relationship? Again, put a mirror here and you'll see exact reflection over there. So these are both enantiomers. Now, I've started with an asymmetric alkene. If you have a symmetric alkene, and I want you to try this out on your own, find out what kind of products you're going to have, all right, for an asymmetric. Is it the same or different? Are you going to get achiral or chiral? All right. What's the minor? Minor, in this case, the regioselectivity could be switched, and you can get the same thing over here, and I'm just going to draw both of them. And you are going to get the nitrogen here, and this will be kind of really minor, and the oxygen on the opposite side. Again, these are also going to be enantiomers, right? So that's for minor product. Again, make sure that you don't confuse the major with the minor. Major, the regiochemistry is such that when you're in a protic environment, you are going to get attack on the most substituted carbon, always, no exceptions to that. So you can see a trend when you have anti-additions here. Formation of the epoxide is syn, but formation of the epoxide followed by ring opening with the amine is anti. Here's another one, formation of the epoxide followed by ring opening with a nucleophile. I mean, we learned lots of nucleophiles when we did SN2. You can use the same nucleophiles here. What would you expect? You see the trend. You form the three-membered ring and you attack from below, you're going to see similar results, right? So let's do this one. Again, you're going to form these first, then you're opening up with a new one, Grignard, RMGX. Grignard is an anion, R minus. R minus is going to go seek a place where it's got least resistance from these bulky groups. So there's less steric here, less steric here. It's going to go bombard on this end and open this up. So when you put your R minus here, you're going to get anti. When you put your R minus here, you're going to get anti. And that's regioselective. Let's draw that out. So here are the two products. One is where you will have the R minus come in from below and attack over here. And so your O minus will go up, RO minus will have an MGX temporarily. Then when you wash with acid, you're going to get an OH over there. H3O plus, which is basically dilute hydrochloric acid or ammonium chloride dilute, and that is going to give you this. Let's say our Grignard R group is a phenol or a benzene. So you will get a benzene here. I'm just going to put pH. pH is benzene. We could do the same thing with this epoxide and have the R group hammer it here, open it up. So we would have your R group coming from the top, and these are going to get pushed down, and your R group would be on the top, pH, and roll over epoxide and make way for your benzene, your huge benzene. What's the relationship? You can see if you put a mirror right here, it's going to be an exact reflection. So these are enantiomers because they're stereoisomers that are non-superimposable. For example, if I flip this over, put it on top, these groups are not going to align. So they are non-superimposable mirror images. And by definition, those are enantiomers. So you see the trend there. And it's a one-to-one raceme because you don't really have any stereoselectivity. You have regioselectivity. You can have a minor product here where for some reason the R minus attacks this carbon. So I'm going to put that as your minor over here. You could get a minor product where your nucleophile attacks the most substituted up and down and roll over that epoxide to the opposite side. So that's one possibility. Then the epoxide can then get protonated by some acid like weak ammonium chloride or acetic acid or sulfuric acid dilute or HCl dilute, some acid that's commonly used. This is going to be a minor product. Now, what about mercuric acetate in the sodium borohydride with A trans? Well, mercury also forms the three-membered ring. And then it's going to be attacked by the water at the most substituted carbon. So you'll get a hydroxyl here. Mercury rolls over and gets kicked out by the hydrogen here. And so that is going to be achiral now. So let's draw that out. So here we have your mercury coming over and it's going to form a triangle there. So it's going to keep that stereochemistry and you're going to get attacked by water above and below. And that's going to get deprotonated. That's just going to get a hydrogen. Just going to put hydrogens here and here. So that's now going to become achiral. In all of these, you got two chiral centers, you see, but here you are losing one of them because you're going to hit that with a hydrogen. Well, you can draw the opposite attack. So if your mercury goes up, your water is going to attack from below and then, do all of those mercury stuff that we looked at in the mechanism. And the configuration here is preserved mainly because you are going to have a mercury holding on to that center. So this is achiral, and same here, achiral. So you only have one chiral center here. So since you have one chiral center, can you have diastereomers? Absolutely not. The only two possibilities, is it the same or is it opposite? If you flip it around, it's not going to go on top of this because these two groups will be switched. Therefore, it's a mirror image. If you put a mirror here, you're going to reflect that right over there. So these two are going to be enantiomers. And it's anti-addition, as you can see, but it starts with a syn. So initial syn followed by an anti. So you will get enantiomers 1-to-1. What would be the minor product? Here too, you have some regioselectivity. So your minor product could be, again, your hydroxyl over here. Well, that would give it a chiral center, but you would have two chiral centers here. So you can have RNS for both chiral centers. So you can have a possibility where you have your hydroxyl over here up and down. And I'm going to put a squiggly line to say that this chiral center can have RNS and the hydrogen can go here, and if the hydrogen goes here, that could also create a chiral center. But your majority would be here, major products here. Sometimes 90% would be here. Okay, this would be a very small minor product. What about HX? Is it going to be different from a GOAC? Well, it is, because hydrogen doesn't hold on to that alkene. So the pi bond is literally broken and it can rotate in any which direction it wants. So here you're going to get a flat carbocation once you have that hydrogen protonate that. And your hydrogen is going to go on this carbon. And once you put your hydrogen here, you have two hydrogens. Remember, you're starting with a hydrogen there. And so therefore, I'm going to put that little tail out there. So you're going to have an A chiral center, and then your carbocation here is going to be whacked by that chloride or bromide, whatever that is. Let's say we have a bromide, and so your bromide can go up here, or your bromide can go down. And both of these are going to be mirror images. So again, enantiomers, and this is a non-stereospecific reaction. Since you have a chiral center, you will have enantiomers, and they're going to be 1-to-1 because the carbocation has equal opportunity to attack from above and below. Now, what about minor product? Would you have any minor? Sure, you can have minor in Markovnikov reactions like this, where it is free rotation. Sometimes you can form the less substituted carbocation, or you can have migrating hydride groups. All kinds of things can happen. So there are lots of possibilities. I'm just going to put a couple out here, and as you can see, I'm really constrained for space. I'm not going to write out every stereoisomer. I'm just going to say that it's possible that the hydrogen can go over here, and for the minor product, and the Br could attack here. And therefore, you can have over here RR, SS, RS, SR, since you can have 4 possibilities there for the 2 chiral centers, 2 to the 2, 4. So you could have your hydrogen migrate over here and to the carbocation. Then you'll have your positive over here. So you can have a possibility where your positive is on that carbon. And then you can have, well, this when the hydrogen that migrated can go up or down, creating a chiral center there. And you can also have your bromide attack here. And it doesn't matter where the bromide attacks, up or down, it's a chiral. So you can have enantiomeric pair for that as well. So these are all minor products. Okay, this is through rearrangement. This would really be the major product because that is also a tertiary, but you could have rearrangements, and you could have, depending on the amount of heat and the conditions, you can have a lot more side products. You can also have alkenes forming, which is basically your E1 reaction. So all of these are possible, and I'm just going to put E1 product here. And E1 product can form here, E1 product can form here. All of these are possibilities for this reaction, plus etc. And I'm drawing both of these here. All of this is going to be common for both the sulfuric acid and the HX E1 products. Same deal with the H2SO4. You'll have your hydrogen attack here, give you a more substituted carbocation, and that's going to be attacked by the water. And so I'm going to draw this out here. You can have the OH attack from above and get deprotonated, or the OH attack from below on that carbocation and get deprotonated, and you have a new chiral center here, and there's a 1-to-1 chance of attacking above and below. They're flat. So here's another example of an enantiomeric pair. All right, so we got quite a few examples here. Here's a hydrogen platinum. What does that do? That's going to put hydrogens on both sides. Okay, so before we go on, after this, I'm going to go back and say, well, what about minor products? Well, minor products could be in H2SO4, and if you heat, you can get alkenes from E1. That's probably the most important one. Or just like before, you could have a hydrogen go over to that carbocation, and you can get OH over here. That's another possibility. So all of these are possible. So I'm just going to put E1 here, and E1 can be, these products over here. Or you can have the hydrogen migrate and you can have a hydroxyl here. And your hydrogen can be up and down, giving you two different enantiomers. That's one possibility. This is going to be more than this because this is tri-substituted and this is tetra-substituted. And you can have a lot more than what I've drawn over here. All right, let's move on to hydrogen platinum. Hydrogen and platinum's just going to sit on here and push those hydrogens onto here. And we did the mechanism. I'm not going to go over that again. If you put a hydrogen here, right on top of this little tail that's wagging over here, that's going to have an achiral center. So you're going to only have a chiral center here when you put that hydrogen. So your hydrogen can go up or your hydrogen can go down. And depending on that, you can get two different products. So you can get hydrogen down and hydrogen up. So hydrogen up. These are both going to be enantiomers, R and S. You have an equal opportunity of attacking from above and below. This center will become achiral. All right, let's move on to the ozonolysis. What does the ozonolysis do? Ozonolysis is a very drastic process that actually severs that sigma bond. This is the only reaction in all of this that we've written that's going to literally chew up that double bond totally. Now, if you had KMnO4 and acid or base and hot, that's also going to chew that up. All right. So let's do the ozone over here, and you're going to put two oxygens over here. So here's your isopropyl and methyl, and the oxygen's going to go right over here. And on the other end, you're going to have hydrogen and ethyl, and you're going to put oxygen over here. Now, what would be the side product here? Well, side product is if you have water here, and it's really hard not to have water because, we're surrounded by so much saturation in the atmosphere. You could have one of these become carboxylic acid. And get broken up. The ketones are hard to hydrolyze. All right. We got one more. Let's do hot. So KMnO4 cold is going to give you the exact same thing as osmium tetroxide. But what if you had KMnO4 hot? That's going to be something completely different. If you had KMnO4 hot, I'm not even going to get into the mechanism because it's going to be so complicated. You are going to have hydroxyls here. So you would take this if you had hot. Again, I'm going to put hot, KMnO4. And we are going to see a oxygen here and a carboxylic group here. Well, did we do all of them or did we do all of them? We did. So on the osmium tetroxide, I've drawn syn. Anti is not a choice for a minor product. So I'm not going to draw a minor product for the osmium tetroxide. All right. Let's do a small summary here. Whenever you have alkenes, you're going to get addition right plunk on that pi bond. What comes in and the configuration of the original alkene would determine the outcomes. All right, guys, so I hope that's a lot to digest. So one of the things that you could do on your part is just take out a notebook, change these to different molecules, and see if you're getting the right products. Okay, that's one thing you could do is change these to different molecules, practice. You got questions, you know where to go. All right, I'll talk to you soon and I will see you. And just for good measure, I will do a cis here as well. See you soon. Bye.